Quick shout out to our lawyers and the team who approved the slides, but also pointed out that we need to recognise Fabrice Bellard as the trademark owner for QEMU, which I thought was a good catch. So I'm going to talk to you very briefly about something that we call QQVP, which stands for Qualcomm's QEMU-based virtual platform. Hopefully it's going to be entertaining. I'm going to keep it quite high level. So the use case is probably the most important thing to understand at this point. Why are we doing all of this? I think you've probably seen slides like this a million times today and over the last week. Essentially, the automotive industry is using an awfully large amount of simulation, both for continual integration and test, potentially for software development, and also, in fact, to get test credits for situations that they can't do in reality. That's true of automotive. It's also actually true of aerospace and defense. It's potentially true for IoT. But the key to that is the ability to run as much as possible of the full stack. So I said I'd keep this light, but I'll go quite quickly because I think most of the people in this room would be very, very bored by this sort of a slide. We are currently sitting at the moment able to virtualize things. That's where we are at the moment, and we're trying to get to the point of being able to handle nested virtualization. That's a point that was probably lost in this slide set. It's actually quite important to us that we are able to indeed run that full stack, including potentially a Gunja hypervisor. And in order to do that, we need to solve some technical issues that this slide set is not going to talk about at all. So the components that we use to build this QQVP device, there are essentially three. We use a language called SystemC, which is a standard provided by IEEE. It's IEEE 1666. It's just had its newest version, SystemC 3.0. I never thought I'd see the day. It finally happened. There is a version of it on GitHub, supported by Accelera, which is a proof of concept or a reference implementation, if you will. That thing is open source and licensed under the Apache license. It is officially the standard for building virtual platforms, theoretically. QEMU, on the other hand, is also an open source project where we build an awful lot of virtual platforms. QEMU, I think you all know and love, so I'm not going to spend too much time explaining what it is. The final part of the story is a set of technologies that we call Qbox, which effectively is a wrapping together of both SystemC and QEMU such that the two things can work reasonably seamlessly together, plus a number of basic components and various things. Our intention is that much of what is in Qbox today either ends up in QEMU or in SystemC. And we are actively working in both communities to make that happen. So the advantages that our customers, we perceive our customers getting out of this, is not just that the virtualization mechanism they're using is quite familiar because people do understand what QEMU looks like and they do understand how to build those things. There's also obviously the quality of using a product like QEMU. And because it's open source, it's very flexible. So we do indeed have customers who take what we do and adjust things inside it to better match their needs. So what does it actually look like when we start building one of these things? So this would be a typical stack, and I think we've seen a million slides like this before as well. But the point is that on the left-hand side, what we're doing is providing a virtual system on chip. In this particular case, one of the 87 families, using this Qbox technology such that the rest of the stack can pretty much remain unchanged. The part that is highlighted in kind of cyan there, was on the original marketing slide deck, and it's the part that we currently have some issues with because having nested virtualization doesn't quite work the way we'd like it to, like at all. Oh, it even changed color dramatically. So, okay, what we're going to show next, and I'm rattling through rather faster than we needed to, but that's okay, because that means you can go to lunch early, which is always good. What we're going to come on to look at is a specific use case. So in this particular case, we're going to have the Qbox infrastructure, which here I'm highlighting in the dark blue. And then underneath that, we've got, or on top of that, if you will, we've got some various different SystemC components. And the advantage here is that SystemC being the standard as aforementioned, if you're an OEM or whatever, you will have other components in your simulation environment that you need to integrate with this thing. Those will typically be in SystemC. And SystemC becomes effectively the glue that pulls all of these things together. So we've got a number of SystemC components here, and then we have a number of QEMU components, including some hexagons and the GIC, and of course the ARMs. And we've got a PCI bus, and indeed we have a number of vert devices. I'm not sure that vert net is in the right place. I think we're using the MMIO one, but it doesn't matter. Finally, just a little note, actually it's also possible that we can, via an RPC link, connect out to FPGA and some other environments. SystemC itself, there are mechanisms by which you can have multiple SystemC kernels connected via RPC as well. So you can potentially distribute this in a number of different ways. Just technically, just so you know, it turns out that everything which is dark blue there, or the kind of orange color, all of the SystemC components run in one single process and one single thread. SystemC has that limitation. So if you want more than one thread in your SystemC environment, you end up having to have multiple processes, which is a bit awkward. That's something that hopefully we might work on in the SystemC community. But anyway, the QEMU part of this is run in separate threads. So there is indeed an issue of switching between threads, and that's kind of what Qbox does. So the next part of the problem is that if you're building these virtual platforms, you kind of have, the virtual platform was all very well and good. And when QEMU was first built, kind of the rest of the world, as it were, was kind of known. It's my PC, I just need to simulate the keyboard or connect to the keyboard and I want my screen. Nowadays, that's exploded rather exponentially, and it actually is probably one of the single biggest problems we have as an industry, is connecting these virtual platforms to the myriad of different things that are needed. Alex earlier was talking about how many other vert devices might be required, and potentially vert camera and things like that. And the issue being, there are a million different ways that those stacks work. So it's quite challenging. There are a number of initiatives to try and make those connections easier. But anyway, let's assume that we would like to simulate a full car and a full stack. Then what we're going to have to do is build some sort of environmental model around our virtual platform, and obviously put some sort of autonomous driving code executing on the virtual platform. So there's, luckily for us, another open source project, which I don't know whether you know about it or not, but there's something called Kala. And Kala is based on, I think, the Steam game engine, if I'm not mistaken. And basically that thing will allow... Unreal game engine. Oh yeah, okay. I don't know, I'm too young, obviously, or the other way around. So the thing here is that it will provide camera images and all of the kind of inputs, as it were, that an autonomous driving application would expect to see from the from the platform. So this is kind of pretty cool, because we can now demonstrate in reality what it's going to look like if you start building a full virtual platform and you start having this sort of environment. You can probably guess that your OEM, your car manufacturer, is probably not using Kala, but all of them know exactly what Kala is, so that it's a kind of a good environment to kind of demonstrate how this all works, and they can then see how they're going to fit their specific environment to it. So, without further ado, I'm giving you 15 minutes. How cool is that?
Thank you, Mark. Yeah, hello. Hello, everyone. So, yeah, at a certain point, Mark approached me and he said, look, can we demonstrate these autonomous driving demo on our virtual platform? And I said, 1 week, 2 weeks, that's not going to happen. Okay, so first of all, you needed to build the Carla client on ARC64 architecture, and I think it wasn't designed for that. So I needed to fix that, and that goes 1 week. Is it playing? Should I just press the button? Oh, that was easy. Okay, so what you can see, what I'm showing here is my development environment, and it's bringing up our QQVP virtual platform, QEMU based, and as you can see, is blazing really fast because it's taking advantage of HVF, which is the Apple hypervisor framework. So bringing up a Fedora 38 image, and in this kind of environment, I was able to do everything, like compiling projects, navigate the internet. I was able to do almost everything I could do on my host operating system. So this was nice. So this is a bunch of applications which are running together and they are interconnected with each other. It's the work of one of our colleagues. On another room, I had a very powerful desktop workstation with a powerful GPU, and that was running the Unreal Carla server. So the 3D work was mostly done on another room, on this workstation, and it was also doing the physics simulation. In this environment, the application on the top left is the Carla client, and this is connecting to the server, and it's basically getting frames at a very high rate. It's not 60 FPS, but I think you can roughly see 20 FPS, which is good enough for, it appears smooth, is smooth enough for a demo. So what it does, it's just a very interesting use case, because this is what happens usually in the automotive use case. You get pictures from the camera, and you're analyzing, processing those frames at a very high rate, and you're trying to figure out what's going on in the scene. You need to know where the road is, whether there are obstacles, what you need to do. So this is analyzed in real time, and comments are emitted, and a reply is sent to the server. So comments like, go ahead, turn left, turn right, or stop the car. So we were quite happy about this demo. I think you have some more slides, Mark.
Oh, I didn't have any more slides. Okay. Yes, I had some technical slides on. All right, I'll give it back to you in a minute.
Yeah.
Okay, so I thought I'd put this slide in before, but never mind, it doesn't matter. Qbox under the hood. It's probably quite interesting to know exactly what's in there. So the key thing here is that we're actually using QEMU almost like a library of components that we can then use in SystemC. And the reason for doing that is, again, because in the environment that we're delivering these models into, SystemC is supposed to be the standard, and it's supposed to be the easy thing that everybody knows how to connect stuff into, and so on and so forth. So this gives us the ability to kind of suck things out of QEMU and provide them in the standard environment, if you will. So we can do that clearly for cores like the ARM A53 or whatever it is. We can also do it for other components like, I don't know what we've got listed here, a UART and things. We can take those SystemC components and provide them as, QEMU components and provide them as SystemC components. I don't know whether I've got, okay, so what does that actually look like? This is some code, we don't really need to look, but the point being that from this is then a piece of SystemC. It's really, really easy. I mean, here we're asking for an RTL 8139 object. It's really easy then in SystemC to just sort of kind of say, I would like to have that object, please, and you'll get that object as a SystemC component. Now we end up with a couple of nifty tricks, if you will, one of which is not quite so nifty because it needs adjusting, but we have some nifty tricks to make it so that that works as smoothly as possible. The first thing we do is when we find memory, we map that memory directly back to QEMU, so QEMU has a memory region which points directly to that memory, such that by the time you're up and running and everything is going as you expect it to go, you're using QEMU exactly as you would do normally, and it's running at the speed that it would normally run at. You effectively, SystemC has provided the pointer, if you will, to the memory region as it would do normally. So for that, we're good. Now there is one other case, particularly for something like a PCI or something like that, where you would really ideally like QEMU to be able to treat the device directly. And it turns out that you have used a QEMU device and you've got there should theoretically be a way of plugging that together. Now, conveniently, the SystemC TLM architecture allows us to have what's called an extension where, and it's an ignorable extension, where you can indicate from one side of the connection to the other any sort of extra magic beans that you want to communicate. And in this case, we communicate back the memory region pointers from the QEMU devices back to QEMU, such that QEMU, again, once we're up and running and everything is going normally, will actually see that device as it would do normally as a normal memory region mapped into its memory map. So by doing both of those two things, we end up, although it looks like it's a field of SystemC models, it actually ends up, having constructed internally a QEMU machine, effectively. Now, this is a much more interesting part of the discussion.
Yeah, thank you. So, can you hear me? All right. So, So for our eternal quest of making things go faster, looking at the CPU, we managed to use KVM or HVF, and I guess Gunia in the future for getting virtualization acceleration. But how about the GPU? So I guess there are various solutions for the GPU, pass-through para-virtualization, and this is what we have been focusing on recently. From the para-virtualization perspective, enters VirtIO GPU, which is a Red Hat standard for a virtual GPU in a virtual machine and guest environment. And that's basically, we have, from the application perspective, nothing changes. You still have the graphics API, so calling either OpenGL or Vulkan. And then the virtual machine exposes this new device, which is the VirtIO GPU, and you need a driver for it. Within the free desktop Mesa umbrella, we have a couple of drivers, which are Virgil and Venus. Respectively, Virgil is the OpenGL driver for the VirtIO GPU, and Venus is the more recent Vulkan driver for the VirtIO GPU. Virgil is older, so it makes use of various ioctls for communicating with the Virt GPU. These are IO controls for creating resources, creating context, creating a buffer for sending commands down to the GPU on the host. But some of these IO controls are probably too much and you probably don't need all of them. Indeed, that's what Venus is doing. It's not using all of them. It's using just a bunch of I/O controls for creating resources, the resources needed for communicating, for bringing up a transport layer, let's call it like that, and then it uses only the execution buffer I/O controls for sending data to the host. So there is this stage where Vulkan commands are serialized into a buffer, and then they are sent down to the host. The host, let's have a look. You have QEMU, which is basically intercepting these I/O controls, these commands, and in turns, it defers and it conveys those commands to a third-party library, which is Virtual Renderer, yet another free desktop project. And according to the context that you have in the guest, you have a backend which is responding to these commands. vrend is the name of the OpenGL backend, which is in turn getting those commands, and it's calling the OpenGL implementation on the host. So you're relying on the OpenGL implementation, and you're actually getting at this point the GPU acceleration. Talking about Vulkan, the backend in Virtual Renderer is called VKR, and it's mostly just getting the comment buffer, it's deserializing these comments, and then it's calling the Vulkan implementation on the host. Okay, so from a graphics perspective, I think we are mostly there. We probably have all we need, but there is one thing that's missing from the picture, which is an OpenCL driver, which is very much used in the automotive industry. So one question you could have is, so why don't you, for example, use a translation layer on top of Vulkan? Like there is this project called CLVK, which gets OpenCL functions and implements them on top of Vulkan. So unfortunately, there are some of our targets don't have all the requirements that Vulkan require. For example, Vulkan requires context init, which is a kernel capability that the VirtIO GPU should have, and is the capability that allows the guest to create different contexts on the host. So you have the ability to create an OpenGL context, and you have the vrend context. Or you have the capability to create a Vulkan context, which is handled by VKR. So in some targets, we don't have this. There is a workaround, like for example, we can create our own third-party library, just like Virtual Renderer, which defaults to Vulkan, for example. So we have a virtIO GPU third-party 2, which which conveys the commands to a different third-party libraries, which defaults to just Vulkan, for example, or OpenCL. But there is still another capability that Venus Vulkan requires, which is shared memory, host-visible shared memory. You should be able to allocate memory on the GPU, and you should be able to make this this memory visible to the CPU. So that's shared memory between the GPU and the CPU. In this case, we don't have this capability, so we needed to find a different solution. So we are basing our OpenCL driver looking at the state of the Virgil driver as of 6 years ago, where we didn't have context in it and we didn't have the host visible capabilities. So basically creating resources for sending commands to the host, and we are trying to serialize the OpenCL commands very much like the Venus driver is doing. And this is a really nice project because it has also a script which generates much of the code for us. It generates code for serializing and deserializing the code based on an XML description of the API. So we were just studying this driver, and most of the job is done by the generation part. We just need to forward this thing. We need to take care of the handle problem, where the graphics API is giving you an object which is a pointer. And this pointer is the referenced in the driver. But if you have a handle which is guest memory, and you're trying to use this handle on the host, then you get segmentation fault because it's a different address space. So this is another problem. We spent a couple of weeks figuring out how Venus does that, and they basically create a mapping between the handle on the guest and a new handle on the host. It's an interesting problem. So eventually we managed to implement all the functions needed for running kernels on the host, and we still don't have shared memory. There are a bunch of functions that rely on shared memory, like mapping a buffer. So unfortunately, we cannot have this yet in those targets, missing those features. But as of May 2024, running kernels on the host, we managed to pass more than 3,000 piglet tests, which is a nice achievement, in my opinion. So I guess that's it. Thank you for listening. So if you... It's going to be open source, right? It's going to be definitely open source. It definitely fits the Virtual Renderer repository and the free desktop repository. So I hope our efforts are going to be nicely met by the community. Thank you. If you have any question, Mark and I will be happy to answer.
Where's lunch?
Okay. Yeah, I'm just wondering, when are you going to submit the OpenCL thing?
Okay, so you know, it's just a matter of time. It's just a matter of waiting for people to allow us to do that. We already have green light for the Virtual Renderer backend, so we are just waiting for the Mesa green light. And we have been just waiting a bit more about that because we are asking for permissions to contribute to more projects than just these OpenCL drivers. We would like to contribute to Mesa from various perspectives.
Okay, so you aren't waiting to improve further your own code, but the code is already there. You just need to have a permission.
Yes, exactly that.
Bon appetit.
Thank you, guys.